solving it, the algebra behind it, and it's just a fun looking geometric problem. So I thought it would make a nice relaxing ASMR video. However, for those who like math, like myself, or enjoy solving math problems, I highly encourage you all to pause the video right now, take a look at the problem as I read it, and try and solve it before I do, and then come back to see if our solutions match, or if we worked it out slightly differently. But yes, before I get into the problem, I want to say thank you to you all so much for the support on my first video back. I think that video has over like 30,000 views already, which is crazy. And it's great to be back. I'm excited to be back doing math problems, solving math papers, teaching you areas of maths, which I'll hopefully do in the next video, and more fun puzzles and games, all to do with maths. So if you do enjoy this style of content or enjoy this video, I'd really appreciate a thumbs up on the video, and subscribe if you want to see more ASMR maths. Anyways, without further ado, let's talk through this problem. So for those of you who are wanting to try this problem with yourself, I haven't used this in a while, I can't quite remember how the highlight feature works. There we go. This problem is a pretty neat geometric problem, as you can see. And in this problem we are told that the largest and the smallest semicircles are concentric. What's the shaded area? And to clarify, the shaded area being this entire blue, sort of funky looking Nike tick. I don't even know if you would call it that, but yeah, that is the area it is basically wanting us to work at. And we're going to go over a few definitions before we start to help those who may be solving it without my help. So firstly, what does concentric mean? Concentric refers to two objects that are typically circles or shapes like circles, hemispheres, semicircles, spheres that have the same center. So, for example, if you had a circle within a circle, like this. This is probably not the greatest diagram. I'm trying to get it to snap to grid, but this center right here is concentric with the smaller circle and the bigger circle, because they both have the same center. So what this means is the bigger semicircle in this and the smallest semicircle have the same center, so that's up to you to work out where that is. And I will give you a couple hints before you start, being that there is a little bit of working with areas of semicircles in this. There is a little bit of algebra in finding unknowns and a tiny bit of Pythagorean theorem, so it should be pretty understandable to follow along. So for those who want to know the solution to how to work out the blue area, stay tuned. And for those who want to work it out on your own, feel free to go for it. But if you're here just to relax and have a good time, I hope you also do. Anyways, let's get started. So I'm going to begin by making this diagram just a little smaller, to the point where I hope you can all still see this. Maybe I'll go a little bit bigger, maybe. There we go. Alright, now let's look through a few things to begin with. So firstly, I want to identify the largest and smallest semicircles to work out where they are concentric. So they are concentric at the same point. Now the largest semicircle I can see is this big one, the goes around like this, and up here. This is the biggest, I mean, I don't know why that made that shape, but that is the biggest semicircle I can see. You guys get the idea. This shape around here. And the smallest semicircle I can see is this tiny little one in here. So that would lead me to believe that the center of these being here say that they are concentric. So if this was made to be one large circle, it would have the center here, which is also the center of the semicircle in here. So let's use that to try and help us work out some facts. Well, the biggest fact that we know is that the area of the blue, which I'm actually going to write in blue, the area that we want to work out in general is going to be equal to this area on the left plus this area on the right. And I'm doing that by splitting it down the middle with this line. So we'll call that the left side plus the right side. And I'm going to keep that there the entire video just so we can refer back to it later on. However, let's start by labeling some things on our diagram. So let's zoom it in a little bit. Now, firstly, there's a few things we can label, and I'm going to do this also in red because we have the value 2, which is from the end of this little tail, or if you like, one of the edge points at the end of the radius of the smallest semicircle to this sort of end point over here. It's on the perimeter of this, or the circumference of this semicircle. So we can see that there is a diameter in here. I might actually grab a smaller pen to do this with, but there is another radius, within here on the smaller semicircle, which I'm going to call lowercase r. Now there is also another radius, and that would be from the center of this semicircle to the edge of this semicircle right there. It's actually, let's just do a straight line like that. Yep, this is also a radius, and that's of the biggest, the largest semicircle, which we can call capital R. Now that is the same at any point along this line, this curve. So we could even connect that, instead of doing it there, we could connect it from here to here. And that's also capital R. Hope you're following along. Now in doing so, we've actually made ourselves a right angled triangle, being that the fact that these meet at the same point, this is going to be right angled. So let's take what we have just drawn and draw it out down here. So let's put that out down here. We're going to have our right angled triangle like so. And we can label it, so the hypotenuse is capital R. The longest side on the other two sides is 2, and the shorter side is R. And of course this is right angled, so we can write it like that. Now using this, we can actually do a little bit of Pythagorean theorem to see if we can help work out what R and capital R are. Now with Pythagoras theorem, we know that c squared is equal to a squared plus b squared. In our case, c squared is capital R. So we have capital R squared is equal to r squared plus 2 squared. r squared and little r squared in terms of 4. Now we can do that by subtracting r squared from both sides, and that gives us capital R squared minus little r squared is equal to 4. So we have some sort of formula to work with. But what can we do with that? Well, let's take a look. Let's go back to solving the area in terms of left and right. I'm going to take our formula here and I'm going to grab it and just pop it. Let's just put it up here. We no longer need any of this. Going back to taking a look at this area that we need to solve, let's work out left plus right. Let's begin with the left side that's blue. So let's do left. Now for the left side, we can see to work out this blue area, if we knew the area of the big semicircle, we just subtract this medium semicircle from that to work that out. So we know it's the area of the big semicircle. I don't even know what to symbolize that. Let's call it big semicircle. Subtract the area of the medium semicircle. Now how do we work them out? Well, there are a couple things we can see from this. The first thing being that we know that the radius of the big semicircle is r. Not 2, it's r. Capital R, sorry. So we already know the area of the big semicircle just by using the area of a circle, which for those who don't remember, the area of a circle is pi r squared. So therefore the area of a semicircle is pi r squared divided by 2, or as I like to write it, pi over 2 and then r squared, except in our case it's not going to be little r squared, it's capital R squared. And that is subtract the area of the medium semicircle. Now what is the area of the medium semicircle? We don't know the radius. We do, however, know the diameter, because the diameter is simply going to be this big R plus the little r, because if you extend that big R round, it's going to go from the center to this line here, from there all the way up to there. That's going to be big R. And then from the center here to the circumference on the point of the smallest semicircle, that's just little r. So the diameter of this medium semicircle is big R plus little r. So we can use that to help us work out the radius, because therefore the radius is going to be big R plus little r divided by 2. Now of course that is all squared, as it's the radius squared, and we're keeping pi over 2. And there we go, we have just worked out the area of the left side. So now it's time to do the same, but for the area on the right side. So let's do right. And similarly, we need the area of the bigger semicircle, subtract the area of let's call it the smallest semicircle. Let's have a little bit of fun and call it area of the bigger semicircle minus the area of the smaller semicircle. Sure. In this case, the bigger semicircle is this one here, and the smaller one is this one here. Now how can we work them out? Well, once again, the area of the bigger semicircle is actually the same as the medium semicircle over here, because we can see again that the radius is going to all squared. And this is all multiplied by pi over 2 because it's a semicircle instead of pi r squared, pi over 2. I do have to apologise, there's been quite a lot of background noise I've had to cut out of this video. So that's the larger semicircle, and we've already worked out the area of the smaller semicircle basically because we have r squared. So this time it's going to be subtract pi over 2 being a semicircle, and then this time it's little r squared. So we now have the area of the left and the area of the right. We can start to put it in what that's going to be for our complete area of the blue. So let us take a few things and get rid of them. Let's get rid of this because we know, whoops, I have not done this in ages, I'm so sorry. I don't know what I've done. Here we go. Let's get rid of that. So that's the area of the left. And this is the area of the right. Oh gosh. Right blue side. So we can now say that the area is going to equal this subtract, or plus, sorry, this. And that is because this is the left and this is the right. So we add them together to get the total area. Now before we add these together, there is one thing we can see. We have a negative pi over 2 capital R plus little r divided by 2 squared, and we have a positive pi over 2 big R plus little r divided by 2 all squared. So we can cancel that out because they're just the same except opposite signs. So it's basically like saying negative x plus x, you know, they just go away. So we're left with the area being equal to, that's horrible, equals, being equal to pi over 2 big R squared minus pi over 2 little r squared. Now how can we work out what this is though? We don't have numbers for capital R and little r. Or do we? If you remember back up here, we said that capital R squared minus little r squared was equal to 4 using this triangle. Can we implement that somehow here? Yes. We have a common factor of pi over 2. So we can say that that is pi over 2 multiplied by r squared minus little r squared. Because when you expand the brackets, that would give you pi over 2 capital R squared minus pi over 2 little r squared. And now we know that this bit in the brackets is 4. So that is going to be equal to pi over 2 times 4. And now this is nice and easy. This is just 4 pi over 2. Or if you prefer, we can write this as 2 pi. And this down here is our final answer. I should also write that that is units squared, whatever that may be. So I'll leave that though, but I'm just implying that this is 2 pi units squared as it is an area. So once again, to recap the entire problem, because that was so much fun, a little bit of working out with Pythagoras to try and work out what r squared and little r squared could be. to